Hello everybody. It's a great pleasure for us today to have Gabriel Dos Reis as our first keynote speaker. I assume maybe some of you know Gabriel, either because of his involvement into the GCC project for so many years, as contributors, as release manager at some point too.
Yeah.
Yes, and maybe for his continuous work on improving the languages. I think like a lot of very interesting new features from C++11 and C++14, so it's too much to actually quote, are coming from Gabriel's work with a lot of other people's. So it's very great to have you there because you made a lot of things possible in the language we are all using there. So Gabriel was, or still is, an assistant professor in Texas A&M, and you recently moved to Microsoft, right? So I hope this presentation will actually help us go into the new state of what you are going to do for C++, and I hope we will enjoy this talk as much as we do. Thank you, Gabriel, for being here.
Thank you very much, Pierre. Thank you very much for the invitation. I'm very pleased to be here. Yes, I joined Microsoft recently, and I used to be release manager and contributor to GCC, and then I moved to the other side. Has been great so far. What I'm going to talk about is mostly forward-looking, supposed to, up running already in the standard, and I thought that this audience was very template-generated programming might be interested in what we might want to add to C++, right? So, my main focus when I was in France, I was still working on programming tools, but when I moved to A&M, working with Vianney, it was really trying to improve development tools, giving developers better tools. And one of the tools that we really, really like is the language. We have the compilers, the linkers, or the editors, but language is what allows us to express our ideas. Sometimes it gets in the way. And one of the things I've been trying to do is to remove those obstacles. The tools we use shape the way we think, right? If you only program in C with macros, you believe macros are the best thing ever invented after bread, right? I don't believe that. So the work that I'm going to talk about is not something that started when I went to Microsoft. It's something I've been working on before joining Microsoft. I'm still working on it on my free time and with some of my students. So essentially, it's all about trying to make templates less scary, right? There are corners in the programming industry. When you say template, they go like this, and then you spend days explaining it. It's really simple. It's much better than macros, voice star, and all this kind of stuff. So the work has been supported by the National Science Foundation, usually support basic research. And interestingly, in the last 5 years, they have been trying to support things that work in the real world, right? You still have to justify the research part. So this is more R&D than pure R. And definitely at Microsoft, we pay a lot of attention to the combination of both R and D. Okay. So the premise of this personal view of programming, right? And I think it is shared by many people I've worked with, Vianney, collaborate with Stepanov, and a bunch of other people, is that good programming is mathematics. So when I say mathematics, I'm not talking about some fairly abstract category theory. I'm talking about very simple, basic things that we learn in high school, right? Basic arithmetic, basic linear algebra, and basic logic. That's all that we need to get most of the stuff done. Okay, So, most of what I do is colored by my background. I started doing symbolic computation. You can think of computer algebra, Maple, Mathematica. Compiler construction is symbolic computation, right? Your compiler is symbolically executing your program and then outputting something else, right? So all of that is symbolic computation. Of course, that naturally got me to generic programming, C++, and in the last 10 years, I've been paying attention and trying to invest a lot of time into trustworthy computing. Can you trust your compiler? So usually, when you write programs, you compile, you run, it doesn't do what you do, you think, you expect, and that's a bug, and usually you blame your own program until you spend, let's say, a week and realize, no, it's not you. Your program's just fine. It is a bloody compiler doing stupid things behind your back. But usually we don't blame the compiler. And you'll be surprised to see how many bugs stupid bugs you can find in compiler. So question to you, can you trust your compiler? Go to GCC website, bug database, and look at the bug number. I think it's in the 60,000, something like that. Some of them are not just bugs, some of them just requests for extensions or documentation, but most of them are real bugs. Some of them obscure, some of them just like, how can that possibly happen? Right. And yes, question? No. In my kind of R&D effort, I decided to look at things that I really care about, which is templates, and in less crowded environment. So we all know that C++ syntax is all it is, and we can do better. And there are other things like anarchic conversions between int, double in both ways, just crazy. So I decided to work on something called Liz. It's just a research programming language where a lot of things have been abstracted. If you look at some other efforts like Stepanov's book, Elements of Programming, you'll see that he really doesn't believe in implicit conversions, especially when it goes in all directions. So before going on, and because you'll see some Greek letters, and please don't get offended, and some Haskells, I first want to make a confession in case there is some kind of doubt, especially given my current affiliation. C++ really, really rocks. It is, okay, this might be preaching to the choir, but it really rocks compared to the alternatives. Okay. And usually you get this feedback. Oh, yeah, but it is an unsafe language, and you can't trust it. I'd like to call that probably not bullshit because it's a family program, but basically that. You can write dependable systems in C++. This is not just a possibility, it is done every day. Okay, and it's even better now that we have almost C++ 14 with all the improvement we got in the language and the Sonar library. You really need to say new or delete directly, right? So you get all your resources managed directly, and you can trust the type system. The core of C++ is actually type safe, right? I'm pretty sure people watching outside or here will challenge me to prove that. Okay, I don't have proof now, and I probably won't have in 10 years, but it is a firm belief that the core of C++ is type safe. And we should try to evangelize that and bring that to the greater world. We shouldn't be shy of making that point. So I just want to make a quick point on trustworthy system. Just make a bold claim. The core of C++ is type safe. I just want to give you some pointers because I've been able to substantiate part of this claim in the more academic world. So, the first thing is that generic programming actually is where you want to go if you want type, safe system, dependable systems, because that forces you to write your code in such a way that you don't make implicit assumptions, right? If you only work in terms of int, well, int support of operations. Is it age, length, and sometimes you multiply length that gets you surface. Is that what you want? Whereas when you express your ideas in the more abstract, sense, using only the minimum requirement that you need, then you're forced to be honest with yourself. Of course, you like something to keep you in check. We don't have that completely yet, right? We're working on that. It's called concept and all of that. But for the most part, when you instantiate and you do something fishy, you get called on, right? You might not get the most friendliest error message, but you'll be told something. So the thing that actually puzzles me is that, so C++ has been around for more than 30 years, right? And a lot of languages come later, and they all, claim to be safer than C++. And very few, if any, have actually taken the real lessons from C++. You have the core semantics, constructors and destructors. Yes. They will go so far as to invent finalizers and try finally, but they won't have destructors, deterministic destructor. I just don't understand why, and it puzzles me. And if we have to take anything out of C++, it is that, constructor and destructor. That is the foundation of anything safety dependable you want to have for C++. Okay. Of course, you have the direct mapping to hardware. That allows you not to leave room to some kind of other runtime in between you and the hardware. And by the way, that runtime, you need to write it in some language, right? You really don't want to use anything other than C++, because you have to trust that other language. So this is a point actually that we made at Popple 2 years ago, that if you look at constructors, destructors, and you pair them properly, so constructor, destructor, they provide a meta protocol, right? In constructor, you can put some arbitrary computation. In destructor, you put some arbitrary computation. But the genius of Biane was that if you look at the meta protocol, it's actually safe, and that's all you need. And that is why all our smart pointers rocks, right? That part is safe. Okay, and before our work, people actually proved that virtual function call, even during construction destruction, is type safe. Okay, and that work was done by some other giants in computational logic and program verification. Okay, and before that, we also proved that when you write your classes, create object, the compiler try to lay out object in memory to, most of them will try to use efficiently, the storage and use very complicated algorithms, whether it's GCC, Clang, VC++, they all do very clever stuff, okay? So we were actually able to prove that for real world algorithm, in a large class of them, they're not just sound, but also safe with respect to construction, destruction, and virtual function dispatch. Okay, so the claim I made earlier that the core semantics of C++ is type safe can be substantiated. Okay, this has been checked by the experts, in the field, until they call me tomorrow and say, "Oh, you know what? Your paper is no longer valid." But I don't believe that. And before I left academia, one of the goals I had was to build a verified C++ compiler. That's, kind of bold project. But the point is that if you want to have people believe you that they can write dependable software, say, air vehicle, those very expensive one-seat vehicles that, when they crash, people die. So if you want people to write software that control them in C++, you really, really want to give them confidence that it is possible. You can't just say, you have to test, but you can't just say test, right? Because the compiler is doing a lot of stuff, you have to give them some assurance, some, formal assurance. And we wanted to build this formally verified C++ compiler. And so the part I was able to do with some of my collaborators, Xavier Leroy, who actually built the similar thing for C, right? It is used by, his compiler is used by Airbus in Europe for many parts. And the next step was actually exception handling. That was quite funny. And I'll have a lot to say probably next year for some talk about exception handling and how to express that and what kind of guarantees we can expect. If you have constructed destructors, you pair that with exception handling, then you have a really, really solid foundation for writing dependable systems. Today, people can't use exceptions in some dependable systems like, avionics, because we do not know how to bound the time it takes to catch an exception. When you turn an exception, we don't have guarantee of when it will be caught, if it is even caught. Right? When you're doing hard real time, you have deadline, you really want to meet that, and we don't know yet how to do that. But it is possible to make, improvements in that field. Now, back to the subject of axiomatic programming. So I designed this, language mostly for research, trying to understand templates and what kind of type system we can have for template. The idea is to have concepts in a way that will be usable by ordinary programmers. When I say ordinary programmers, I mean you shouldn't need to obtain a degree and master's or PhD in template before you can write modern C++. Your first class of C++, you should be able to use templates and not even need to understand all the rules. When we were at the NM, Biane had this course, for freshmen on C++. You know what? The very first class, they will use vector of 8. Way before they even hear about malloc or new or any of those things, right? The first container they will use is vector. And they use templates, solve those things before you understand what a template is, how you can define it. Okay, so we really wanted to improve templates. And I suppose today there's a lot of talks on templates. And last year probably had Andrew Sutton talk about concept light. So what I'm going to say today hopefully doesn't overlap with any of the talks today, neither the talk of Andrew. So the thing that I really wanted to do is to integrate automated deduction. Why? The reason is that when I look at a lot of template code, it looks to me as people spend a lot of time trying to tell the compiler what it already knows, right? and sometimes they get it wrong. But because we have so many rules and conversions, sometimes compilers say, oh no, wait, sometimes like, okay, I can make it work, but not doing what you really want. So a good way to take that complexity out of the picture is to make the compiler smarter, deduce things it already knows. We have template argument deduction, but the way we program with template is that you have this database, template specializations, and there is only one level of things. You can query template, how you associate template argument, but the compiler is not smart enough, or rather I should say the language rules currently are not designed to allow the compiler to make chains of deduction from a set of knowledge it already has. And for that to happen, I really wanted to have a form of automated deduction. I've heard people say that, oh, if it's happening implicitly, then the compiler will do something in my back that I didn't intend. I don't know exactly how to interpret that, because sometimes, not just because you write it explicitly means that it is correct. I don't trust any reinterpret cast, okay? And that you have to write it explicitly, and I don't trust any of them. Even when I'm given the code and justification, I'm always suspicious, but that it won't do what I want. I tend to trust more template argument deductions. But is that me? No. When I call, find to iterators from second container and output and deduce correctly that, well, I have output, input, I don't really need to tell again, compiling some other forms so I can have it checked. That's just fine. Okay, but when I have to supply explicit template arguments, I'm crazy. Maybe I'm not smart enough, at probably 8. But saying something very explicitly when a compiler already knows it is a good way to get yourself caught into, some hard to debug situations. And the other thing is that I really want to break with conventional type checking. What do I mean by that? I will give you 2 examples of what I call conventional type checking, and hopefully you get a sense. We do a lot of those in C++, and to move forward, you really need to add something new to the picture. So briefly, I'll just tell you, so these are students who have been working with me since I started. So Carla was the first student on the project. She wrote the parser and started the elaborator. And then Eric came in and wrote some libraries and also worked on the compiler. Jason started about 2 years ago with his PhD. So he has network background. He's electrical engineer, and he looked at it and said, "Oh, this is all great, but I have no use for your axiomatic stuff." Oh, wait a minute. Before he started, he worked on startup, funding his own startup, worked on network protocols, and you know about had Blade, but before that had a bunch of other stuff. And one of the realizations he came to was that first, most of the network protocols are written in C, and they have bugs that can be there for 20, 30 years because they get found, right? And it doesn't depend only on how good you are. Every programmer, no matter how smart he is, has some error rate. At some point, you get some bug there. It is just mechanic or whatever it is. You just keep at it. At some point, you get some bug slip. Okay, everybody has error rate, and those are very costly. Even when you get experts together to look at the same piece of code, they can't always catch some of the egregious bugs, right? And so he wanted to include deduction and checking into these systems, and so that led to what we call dependent types. And originally, when I studied Liz, I was using exactly the grammar that's in Stefanov's book. And after Jason, in the summer 2012, I had to rewrite the parser because using single syntax for template dependent types is very awkward. Just for the same reasons that we introduced the new declaration syntax in C++, where you say auto function parameters and you say return type, so that you can use some parameters in a return type, basically for the same reason. And Jordan was the latest in the team, and he's very helpful with the library and also the compiler. Now, the project didn't actually came to fruition till Alex released this book. I remember back in 2007 at Hopple 3, I was given by Paul a draft of the book, and it changed between 2007 and 2009. It was when book was published. And I went to say, okay, wait a minute. I think if we want to have concept for C++, and at the time, the concept were already, C++ concept were already going down, I think it must resemble this. And then for me, the question was, can I type check this? So that was when we started, and Carla started writing the parser, studying the rules, and had a lot of conversations with Paul. Shen was also involved, and so forth. But this was actually for me, the catalyzer for pushing this project forward. So, what do I call commercial type checking? Well, this one actually is very popular, right? C++ made object-oriented mainstream. It took it from the labs into the street to everybody. The way it works is essentially you have some pointer to data of unknown size. You don't know the size of the data that the pointer is pointing to, and you have some table of operations. Okay, and then you separate concern interface, definition, the use, and the roles are set up so that everything just works fine. We know how this works, okay? And if we want to make advancement with our template system, we shouldn't end up with this. Because we already have this. We have tried several times to make it work. It just doesn't deliver what STL allows us to do. Okay, so this is one example of conventional type checking that I think we shouldn't end up with. If we end up with this, then we have failed. Again. The other one really comes from functional programming community. Ever since I've been working on concept, I'm always called on conferences. Oh, why don't you just take Haskell type classes? And then I have to patiently explain that, well, Haskell has very beautiful type system that doesn't work with C++. And then you say, why not? And then you go and explain, well, Haskell requires you to say, but the fundamental thing is that the type system of Haskell is beautiful, it's great. But it is not the solution to the problems we have. The problem we have in C++ is that we want the ability to write specification independently of use. The core of the Haskell type system is what we call a Hindley-Milner system. The principle is this. You write your function definition. Don't put type anywhere. The compiler will deduce the type for you. The fact that the compiler deduces the type for you is also a proof that somehow your program is correct. It doesn't say it is right? Just say it's correct. The operations will do the operations. You won't pretend that a string is an integer, right? You won't do any of those things. It will be type correct, but not necessarily right. Furthermore, it starts from the principle that the implementation is the specification, right? Write a function definition will deduce the type for you. A type for a function is always a summary. It is a specification. It's a crude approximation of what the function is supposed to do. So give me the implementation, I'll tell you what the specification is. How do I know my specification is actually right for the problem I want to solve? The Hindley-Milner system doesn't solve that. Okay, it is really good. Okay, and as a matter of fact, if you look at C++ template system, we actually have part of it that looks like that. But the entire system can't be that. You must be able to separate definitions from specifications and from use. Okay, so that we can check what's going on. Now, what's Haskell? You probably want to make a point. Just to illustrate, the previous slide was a bit abstract, but to illustrate this idea of Hindley-Milner type checking, so imagine that the blue line would be deduced by the compiler. What you write is, in black, in product, right? So here we have a function filter. What it does is you give it a predicate and a list, and it will return a list of all the items that satisfy the predicate. So obviously, if you're trying to filter an empty list, it's an empty list. That's what the first line says. So in Haskell, you just write equations to state what you want. And the second line is saying, well, if I don't have an empty list, then I have at least a list of one element that is prepended to an existing list. So I have a list of x and some x's, right? And the colon there is just a way to decompose a list into head and tail, right? So imagine you have an iterator. When you reference the iterator, you get the head, but you have to increment to get the tail, and the colon is somehow an abstraction of that idea. So when I'm filtering the list, if the list is not empty, I have at least one element. So what I'll do is that I'll test the predicates on the head. If the predicate holds true, then, well, I'll keep that element. And then recursively, I'll filter the rest of the list. Otherwise, I'll just go onto the tail. Very simple. You write what you want in 2 or 3 lines, and it reads like English. Fantastic. And then you run a compiler, it comes back and says, hey, the specification is you take a predicate, something from, a predicate that takes some element of type A, returns a bool, and a list. So bracket A means list of A's, and returns list of A's, right? So this is Hindley-Miller system. And because it can do this for you, it's really fantastic. And interestingly, to make this happen, you need only 5 rules. The type checking rules, we have 5, okay? And it is a deductive system. It's a logical system. You write a compiler with that logical system, and you submit any statement, so any function definition. It will come back with either error, doesn't make sense, oh yeah, it makes sense, and here is what it's supposed to do. Okay. But this is not sufficient for C++. Okay. So when people say Haskell type classes, what they mean is essentially, take Hindley-Miller system, and then from time to time, you want to overload some operations. Probably on the previous slide, the point I want to make is that for this system to work, there is an implicit assumption that every single symbol in your program has a unique interpretation. So here, brackets means always list. And colon, that way, always means append or prepend, right? Because every symbol has a unique interpretation, that is how the compiler with this deductive system is able to work out, right? Because it doesn't know, ABS, is it ABS of int, double, there is no ambiguity. Okay, and this is one of the reasons why it doesn't work, and it doesn't support overloading. So when Haskell folks wanted overloading, they said, well, okay, we'll still maintain the claim that you only need to provide a definition, and we'll deduce the specification for you, the type for you. But for that, you also need to declare something what they call class. So what they call class is not the same as in C++. So what they call class is just a collection of types that happen to share some common operations that are overloaded, right? So here you say that, well, we have a class EQ, key of A, all the type A that happen to be equality comparable, they must somehow provide an operation that compare them to elements for equality and non-equality. Now, once you have this, and you write these 2 lines, so forget about the first line, get just these 2 lines, the compiler will be able to deduce for you the type of a function. The way it does it is just like previously, except that now we are also using some symbols that put constraints on what the type A could possibly be. And then the compiler will go back and say, okay, well, this member function that tests whether an element is in the list works only if the type of the items happen to supply an equality operator. Okay. But when you look carefully, again, it is bottom up. Why? It's not top down. It's always bottom up. yeah, please.
Shouldn't you recurse?
Oh, yes, I should recurse here. You're right. Yeah, it's false. It should be a member of, yeah. So this was type check, but not run. and made my point. Thank you. So this is the bug. It should not be false. It should be a member of X, Y's. But again, it is bottom up. Okay, that's all. It does. And for C++, we want the ability to specify what the find function would be without having to supply the implementation. Okay, for various reasons, good reasons. Now, it is what has been, if you want to have a career in academia, don't work on C++. Okay, that's an exaggeration, but close enough. Please use Hindley Miller and Eversoft and just tweak a little bit, and you'll have tons of papers and wonderful career. I don't believe that it scales to handle correctly the size of the problems that we face when building software with C++. Okay, I'm pretty sure I'll make some enemies out there, but and I would like to be proven wrong. But so far, I haven't seen any sizable program to the take Chrome, take Internet Explorer, take Office. They are written in C++. And the infrastructure behind, the number of lines of code behind is not comparable to anything I've seen so far for Haskell or for any other ML system. Doesn't mean that they're bad, just that if you want to scale, I believe you need something other than Hindley Miller. Now, what is that thing different that I would like to see? Well, look at this picture. We have some sphere and a curve, some algebraic curves, degree, 42, 43, I can remember. And then there's a lot of properties. And one question is, well, the first thing is, if you want to represent these two objects in your program, you'll need some form of data structure. And mathematicians like to use, parameterization, right? If you're doing graphics, you like to parameterize so that you can shed the proper lights and reflects and that kind of stuff. And sometimes they would just like to have slightly different representation, what they call implicit equations, right? So for a sphere, for example, this is a mathematical theorem. It says that you cannot represent a sphere with less than 2 parameterization. If you take only 1 parameterization, there will be at least 1 point you cannot reach. So you need at least 2 charts to represent a sphere parametrically. That's a mathematical theorem. And because they're going to overlap, you also need some, coherence, relations that you have to check and all of that. Okay? But if you go with implicit equations, all you have to say is that, a sphere is all the points at a fixed, given distance from a fixed point, right? X squared plus Y squared plus Z squared equal R squared. That's all you need to say. Just one equation for a sphere. But if you want parametrically, you need at least 2 charts. Otherwise, you miss 1 point. That's geometry. Not my claim, it's geometry claim. Now, the question I want to ask you is, if you want your programs to be simple, wouldn't you also want to have fewer template parameters in your programs? Is that desirable? I would think so. If you don't believe me, I will show you a fragment of real-world code that's distributed, used by a lot of people, almost every C++ programmer. And I would like to know whether you really want to write that class. Okay. Any questions so far? No. Okay. So this is just some going, not too much math. So working with implicit functions is really nice because it gives you a very global view of what's going on. So if you're developing a large-scale system, software, you want to have a concise way of talking about the global behavior. And then sometimes you want to dive very deep into components. So if you want this analogy, you want implicit functions that allow you to have a global view of what your system is doing, and then you want to have parameterized template, whatever they are, so that you can control locally what's going on. Okay. Now, this is what worries me. I'm not kidding. 2 years ago, that class had actually 13 template parameters. As of this morning, it has only 10. Okay, so this is the class template. Imagine you have a function in your API. It has 10 parameters. We have many of those. They come from C, right? So all of them are type names, right? So imagine you have this function, takes 10 parameters. They are all int. Tell me, when do you know that you're supplying the parameters or the arguments in the right order?
You don't.
You don't. That worries me. So this is used as implementation of hash table in popular standard library implementations. Okay, and so so this of course is invalid. So I had to take away the template argument there so that it can fit on the slides. Okay, but you can Google this or Bing this. And find where it comes from. This worries me. This is what you get when you insist that you need to control the parameters that you need to write your software. Sometimes you don't have a choice, but I do believe this is going too far. Okay, and I know some of my friends will be unhappy with me, but that's my belief. Okay, so what I would like to see is a top-down. So we saw earlier that the Linux system is bottom-up view, right? You build things up and you discover something. What I would like is a system that also allows to have a top-down view where you state global properties of what you want, and then you figure out later on what really implements the property. Okay. And to some degree, this is in Stepanov's book. Of course, he didn't start with axioms. He started with real algorithms and work his way out. Okay, here are the real requirements that make that parameterize the algorithms. And if I weaken these assumptions, then I can get these. If I strengthen, I can get the other stuff. So that's why we get input iterator, forward iterator, random access iterators. But the whole thing started with real algorithms, and then you work your way out by looking at smaller components. So in C++, we know how to state this, right? Have sort function, and then you have comparator, and most of the time it works, except when it doesn't. When it doesn't, people get obscure error message, and it would be nice. Very good. If we could actually state the relationship between the comparator and the iterator that we're using to delimit the sequence we want to solve. As written, they are just completely two independent entities, right? They don't have any relationship. That's not true, right? The comparator must be able to take something from the value type, things you dereference from the iterator. So there is some relationship. And how to state this has been, in previous decade, a lot of people pour energy, efforts, and brain power into it, and we didn't succeed. We're trying again. So what I would like, again, to have is this top-down view, what called final co-algebra. It's technical term. Previous view is initial algebra. And if you look at the Stefanos book, it's actually remarkable because it has only about 5 primitives that allow you to do this. Another observation is, if you look at the STL, it doesn't actually construct anything, right? Most of the time, it asks for something. Oh, am I at the end? If not, then please move me again. Give me the value. But it doesn't actually construct objects. When it needs to construct object, it asks, where should I place this object? That's the allocator, right? And then please give me the constructor. But it doesn't actually, construct things internally. Most of the time. Sorry about that. Is it working? Yeah. Most of the time, it just asks questions and work with the answers. So it is very different from the object-oriented view, right? Object-oriented view, they really want you to say, what is the type of this object? That's not a really meaningful question. From development perspective, I think the better question we should be asking is, how can I use this object? That's all that matters. And the STL works that way. So if you look at the STL and the elements, it has about 5 basic notions. A bit like Euclid, right, with his 5 actions. The first thing is, can I call this thing? So the notion of function. This is simplification. Stefano has actually a notion of procedure, and I'm just simplifying here, going directly to functions. And the next thing is, if you want to call it, so how many arguments should I supply? So that is the arity. It doesn't actually say that how many arguments the function takes. You just say, how many should I supply? So the function could, the callable thing can have default argument and that kind of stuff. And from time to time, you want to bridge the gap. So what should be the type of thing that should bring into that position? That's the input type. And then sometimes you want to say, what should I take out? For example, if you want to have iterate something, you want to put in something that has the same time as what gets out. Okay, and you want to state relations. You want to state that those 2 types are the same. So that's the equality. Okay, these 5 primitives were the only ones that I needed to construct the list system, the core type checking part of the system. So I find that remarkable. And to give you an example, so here, imagine I have a function type takes a vector, so you point a vector, so you plant, arrows at places that you get these vector fields. So it does satisfy the notion of, function. It's arity 2, and input type at, first position is point, second position is vector, and the code domain, what you get out is this vector field. If you plant these arrows in your field, you get a vector field, okay? Now, then he goes on to define the notion of homogeneous function. So if you look at the book, I really want you to get a copy of this book. I have no stock in the book, okay? So, but I do believe it is a book that everybody should have. At least everybody in this room should have. And everybody interested in C++, writing programs should read that book. So it says that homogeneous function is a function that takes at least one argument. And all the arguments are of the same type. I could go and express the same thing by using local coordinates, like template parameters, or I could just state that. So the first line says, I should take at least one argument. And the second line is just a logical statement saying that all input type are the same. So see here, I'm just using equal between 2 types. That is fine, okay? The fact that we can't use equal on types in C++ it is not something fundamental. It is just syntax issue. Okay. Hopefully one day we'll solve it. I'm sorry?
I said we have, instead of equal, we have is same.
Yeah, and then, yeah. So an example of homogeneous function is when you take the distance, function distance, that compute distance between 2 points, right? You get 2 points, homogeneous, and then you get, double. So the return type doesn't need to be same as input type. A non-homogeneous function is one that will allow you to translate a point by some vector, right? So you need a point and vector, you get to another point. Okay, so if you look at this condition, it says that all input type are the same. So that make it possible to define that common type. So in Lisp, you can actually define a function. So think that this is some kind of type function, right? That's what it is. In Lisp, they evaluate it the same way you evaluate const express functions. And I really wish we had a simple syntax in C++. Then, we have template aliases, but I wish we had more direct notation. And all of these things are actually evaluated at compile time when you compile in Lisp program, and they are needed too because you need to reduce all these things. So the next thing that Stefano defined is the notion of operation. It says that, an operation is a homogeneous function for which the input type, the domain, is the same as codomain. I say that, right? That's what it says. It says the concept of operation is the one where you take all homogeneous functions and the codomain is the same as the domain. That's all. So far, none of this has said anything about how the operation is represented. Is it real executable code like you have in C, or is it function objects, or is it some other lambda stuff? It doesn't say anything like that. But if you want to express this directly in C++, with template parameters, you'll have to go through hoops to avoid saying anything at all about the actual representation. And sometimes I think you can't. Right? We have this callable invoke in the standard library that says a lot of things without actually telling you what it is. Okay. So, and a binary operation, now we're getting more concrete, right? We're fixing the number of arguments and say, the arity must be 2. Again, with only these statements, we are able to type check Lisp program, okay? So Lisp program, imagine the programs in Stefano's book. Okay, I'm just using slightly different syntax. The real problem doesn't change at all. As I said, I started with the syntax in the book, only changed this notation when we started taking dependent type seriously. So here, define operation. So imagine this is just a funny syntax for templates, right? So have function template square that takes an x of type const reference to the domain and the operation that we want to square, and just apply f to xx. This is almost exactly the program in Stefano's book. Only the syntax changed, but everything else stays the same. We can type check this, okay, with only these axioms. This is what I call axiomatic programming. You don't say anything about a concrete representation. You only say what you intend to have. So it's kind of declarative form, but it is really axiomatic. And if you look at the axioms carefully, they are actually constructive. Okay, again, this goes back to Euclid. Right? When we talk about Euclidean geometry and all of that, all his axioms, they are all constructive. It's quite interesting. So how, there's this get type check. So here you see that we're actually using a concept as a type. And we're going to have this in Concept Life, where you can use a unary concept as a type. So the idea is that when you have that, you have implicitly some type, right? So alpha here, this big dot just means type name, think type name. So synthesize some invalid type. It has to obey the predicates that it is a binary operator. So you fix that type. And then you use it now in the actual function type. So you see here the actual function type is a const reference to the domain of that type T, and that type T, which is the type of the operation, and then you get back the domain of the operation type. Okay. So this gets type checked and internally stored in the data structure that represents this. I'm just putting the mathematical notation for it, but the actual data structure, yes?
In that example, F is a keyword, Fx of x is a keyword, and the F itself.
So this declares a parameter.
No, I can't.
Ref is a keyword that says reference.
I skipped over that, I'm sorry.
Oh, goodness. And so it's just applying this operation to a value from its domain. Thanks. So I can use this for, say earlier, do I have code? No, like in C. So that would be the multiplication function, the first function. Or do I have a function object? So I didn't define it, didn't have a slide to define. But imagine this is plus angle bracket, not square bracket. So in Lee's notation, this the equivalent of template bracket. So plus angle bracket, int, and you instantiate. The curlies in Lee's are just constructors, right? You probably know that we introduce uniform initialization syntax in C++ using braces. We just think that braces are operators. In Lee's they are, in C++ they are not. But if you had the syntax, that's really what it is. So we just create some function object. So the square function works for objects and pointer to codes without any assumption of the representation. All that is needed are the properties. How can I use this as opposed to what it is? Okay. So concepts are not just syntactic requirements. Previously we only had syntax. They also have semantics, right? And if you look at Stefanov's book, he spent a great amount of time on semantics, and that's what he uses to actually refine his algorithms. So in Lee's, you can state semantics properties as axioms. So for example, if you want to have associativity, we all know that at least string concatenation is associative. It is not commutative, but it's associative, right?
You have f of A, B, and then f of A, B.
C. It should be BC. So this one is type checked and not verified. Okay. So another bug, this should be B and that one should be C. Thanks. So all dangers of type checking and not verified. So the associativity just means, well, if, usually F will be some binary operator, right? Thanks. GCD is not operator, but it's one of those things we actually use. And they're actually useful. The associativity is useful if you're trying to decompose, you're going to reduce your string concatenation or GCD of a sequence of elements. You probably want to split into pieces and then concatenate them individually and concatenate the result. And you want to guarantee that wouldn't change the result of the operation if you just did naively. So that's what associativity is all about. And then in this you can assert. So this one is not checked, right? This is the equivalent of reinterpret cast, right? You say, oh, trust me, I know this one is associative. So this is probably one of the places where I'm not bold enough. I could say, oh, the compiler has to prove everything. Then I won't be able to do anything at all, right? Because it requires just so much that you can prove automatically. But it is one of those places where you tell the compiler, I know these facts to be true. Please use them. Now you run the risk of having some inconsistent system in the end. Because there are syntax specific for those, you can actually, if you really want to have proof for them, you can extract them to some theorem prover outside the list, because I really don't want to require programmers to start doing proofs in program and do that, get that proof if you want it. So the semantics properties list are used for, during overall resolution when there is, a tie or there's a constraint that something has to be there. So concretely, an assumption like this is stored in a database, just like we store template specializations in database and query when needed. Okay, so here's a complete another example that uses the notion of associated values. If you look at what we call monoid operations, for example, now they will be associative, but then it will also be a distinguished element that wouldn't actually do anything to element when you combine them. So plus would be 0, multiplication would be 1. If you take GCD, it would be 0. So you have many operations like that in real-world computing that have these kind of monoids neutral elements. So here, just stating that the notion of neutral values, it's an axiom. So anything that's defined as axiom is taken as an axiom. The notion is that for every element in the domain of the operation, this element E is such that so when you compose X with E with that operation, you get X back. And if you compose the other way, you also get X back. So this is another place where I don't use equality, I use equivalence. Because, again, I'm starting from the C++ core semantics. You want to interchange values. You don't necessarily have equality defined by a user for you, but you want the ability to interchange value. And this is what I call behavioral equivalence. So a concrete example of this is, imagine you have a function that returns some value, let's say a string. And you return a string. So in the body, you say return S, right? It's some string that you compute and you want to return it. That string that you're returning, you want to get the same value from the outside, from the caller, right? But for a bad example, string has equal, but what you get, what is being returned is the same as in the outside. And being able to return a value doesn't require you to have equal. Okay, so that's what I call behavioral equivalence. It is rooted in C++. Okay, and that's what this equivalence is for. It's really behavioral equivalence. Whatever I get there is what I want there, and they may or may not be equal, right? So if you take a better example, would be none, not a number. Not numbers, they don't compare equal, not even to themselves, right? So if you return a none from your function, you really want to get that same none on the outside. You don't want it bit to just flip, on whim. So that is behavioral equivalence. Question? Yes.
So you're using equivalence over here, and this is something that couldn't be checked at compile time. And the notation that you're using here is necessarily only going to be a subset of the kind of axioms that you might have. Some of them might have to be written as a like this is a Turing complete function. So I wonder what the use is to have this subset of axioms that you can write in this notation that aren't checked.
Okay, good question. So how much so the question is, when you look at this axiom, it is written in a certain logical language, using here equivalence that it just defines behavioral equivalence, not logical equivalence. And so that is a restriction of what could be possibly written. And the question is how a user would be able to write something that's bigger than what that logical language allows. That's a very good question, one that I never found a good answer for. I had long debate with Bjarne when we were back in Texas. So here I use behavioral equivalence, but it is not a requirement. You could use equality if that is what you want, right? And it will be checked at runtime because it is no longer an operation that is internalized by the compiler, but something that happens at runtime. At this point, I do not know, and I suspect more, experiments will tell me where I should put the bar. The one thing we have to keep in mind is that first, so all of the concepts are written in first-order logic, and first-order logic is undecidable. And one of the things I was trying is to bring in automated deduction. So I must have decision procedure for the logical language. I'm not too precise on the slide, but when you get to write the type rules, you have to be more precise, right? So for the logical, for example, do I use all the integers? The answer is no. I use only Presburger arithmetic, and that is sufficient for dealing with arity and everything else, right? So Presburger arithmetic is you start with 0, you can add 1 all the time, you can compare things. You cannot multiply by arbitrary number. You can multiply by a constant number, because if you multiply by 2, for example, it's just adding the same thing twice. If you multiply by 5, you are just adding 5 times. But there is no arbitrary multiplication. And that theory is decidable. It is sufficient to handle almost everything that is in Stefanos' book. The one thing that I don't know how to handle, because it's not decidable, is the ring theory that is part of the book, but he hasn't spent too much time on it. That's great. And for iterators, Presburger arithmetic is all you need. So the short answer is we need more experiments and more feedback. And that's a great question. Thanks. Yes?
Do you support operations that have multiple domains? Like, for example, plus has int as a domain or double as a domain.
So that will be overloading, yes. So you can overload symbols in LIS.
So can I, for...
Oh, sorry. The question was, The question was, do I support operations with different domains? And by different domains here, mean if you take plus, for example, you have plus on integers, plus on doubles, plus on strings, and is that supported? And the answer is yes. You had follow-up question?
I was just curious how that worked.
Oh, so question, how does it work? So when you call the function neutral value, the axiom neutral value, here, in this situation, we have overloaded operation. It will be ambiguous. But if you use the @ symbol from the previous slide, you can use the @ symbol to restrict the type of an ambiguous symbol. So, for example, this is construction. It is ambiguous, but I'm saying construction at the type plus of int. So that restricts the expression and make it very unambiguous. So the same thing is, oops, why? The same thing happens here. When you use the axiom neutral value over something, if that something is ambiguous, you just use the at notation, like some at int, comma, int gives int, and you can think of it as the equivalent of static cast in C++ to resolve an ambiguous function symbol. Okay?
One more question, Gavin.
Yes.
So you can declare these named axioms, you can define them, you can assert them, and you do function dispatch based on them. But you never actually, as far as I can tell, use the definition of the axiom to check the properties. So what's the point of actually defining them?
Very good question. So the question is, so if you've been paying attention, you notice that you can define axioms. You can use them to assert properties that go into databases, but the bodies of the axioms are not actually run in. I haven't shown an example where they're running anyway, and so could I just dispense with the body and just have some dummy name? The answer to that is, in fact, in the fuller development, when you use assert these axioms, you can extract them on the side, right? And try to check whether they're correct. But the checking is not done by the compiler itself, because although I wanted to have automated deduction, the compiler, I didn't want to turn it into a full-blown theorem prover. Okay? So the body of the axiom themselves are not run directly in the code, but you can use them on the side to check for the consistency and give extra confidence to your program. So it is not completely useless. If you do not extract them, yeah, they don't exist, just like some random tag. But the idea is you express the actual semantics in the program, and with the aid of additional tools, you bring greater confidence to the system.
So what's the difference between these axioms and comments?
What is the difference between these axioms and the comments? The difference is quite obvious. The comments are white spaces. These axioms, they are not white spaces. You can extract them.
You can extract comments. If you have a tool, you can extract comments. I mean, you have to have an external tool to extract these axioms, and then only then you can do something.
Yeah, so in the comment, what you could put in the comment, the body of these axioms use the language itself, right? So with this additional...
So it's the syntax of these axioms.
The syntax is checked, plus you have elaboration, right? So these are the syntax, type checking rules, and you can actually... so what I call by elaboration is when you can generate code, right? It is just not executable. You can generate code for this every time you assert it. So you can say, if you wanted to inject, for example, debugging, you're doing debugging, you can say, well, put a watch point here. Every time they run these actions, right? The pre and post condition, people like to do programming by contract and check.
Essentially, you can generate tests, runtime tests.
Yes.
From these.
Yeah, but they are not inserted by default in the. Yes, exactly. Yeah, and actually in the last slide I had a point on that, but that's very valid and interesting point. Thanks. So one question is, I've done all these kind of obfuscation, and what do we get out of it? The first thing is that we have a higher level specification of what we want, right? It just gives a glimpse into what is possible. Within the C++, framework, I use different syntax of that, but the core is there. The core semantics is there. So the actions give you this explicit statement of properties. If you wanted to have more confidence in the software, you can actually, generate, use external tools, to improvers, or and get more confidence. The other thing is, I didn't confess to this when I started, which is that I hate threats. They should have never existed. They existed only because we didn't know how to express things earlier, and we should aim to eliminate those threats. So these ideas, I've tried them in two different frameworks. So before writing the Liz system, I already had this computer algebra system called Axiom, right? So one of the students was, okay, can we use these additional semantics properties to do automatic parallelization, or just controlling threads and so forth. And it's actually quite enlightening. It was very positive, and it was presented at ISAC in 2011. And so Eric Katzen was the student who really wanted to learn more about generic programming, and teaching him generic programming through these, ALEC style, statements of properties and so forth, and reasoning about the algorithm based only on what is assumed, was much more positive than other attempts I've done earlier by just, look at these requirements from the standard library, and this is what get. Because now, if I make a mistake like I've made, then you can call me on it, right? You can argue your way around colors, right? I don't like blue, I prefer red. When you put the axioms, you don't mess with the facts. You right or you're wrong, but not, I don't like your arguments. For me, the most important thing, especially since I started this for C++ concept, was to give feedback to the community about what we can try today and we know can work. And so, for example, using concept as just the type of something, what we call shorthand notation, and using predicates and do simple deduction. That has made its way into Andrew Sutton's implementation. And his implementation out there you can try, but originally most of the work were done in Liz. Of course, at the time as academics, you need to have, formal semantics. And even today, even I'm not academic, development organization, we do static analysis. And you do need precise rules that you can check. And if you find bugs, you have to explain why you think it is a bug. And you have to explain to the dev why something is wrong. So you do need, these formal statements. So I'm going to skip on this, how it works, and I don't know how much time is left. 10 minutes. So, okay, I'm just going to skip a little bit over the Greek stuff and just show you this example. So when I have this statement like this, how does the compiler turn it into something that is executable inside a compiler? So it is actually very simple. So the first thing I think I explained earlier, you see the function concept used as a type. What we do first is to synthesize a type variable and say that it has to satisfy these predicates, this substitute in there, and this logical formula. Now, if you look at this logical formula, it is in what I called earlier the theory of Pressburger arithmetic, so it is decidable. Okay, there are a lot of algorithms there. There is a theorem that says that the best algorithm will have double exponential complexity. Don't get scared. Okay, in practice, we don't see that. So it actually happens. So this thing is actually very efficient. So most of the arithmetic theory, you know, you can squeeze them into this arithmetic. And the other thing is, that I want to say is that this Pressburger arithmetic, it is already in your compiler today. The optimizers, they use it, right? When you're doing automatic vectorization and you have nested loops and they want to flip things around, there is a common method based on simplex or linear programming, but they all go back to Pressburger arithmetic, which is decidable. And they use that today. So this is not like, bringing some huge theorem prover into your compiler. All we're saying here is that it's already there. Just make it work with the technology, make it slightly more generic so that it can work with the type system. I saw you had a question? Yes.
I don't really see a difference between the top and the bottom.
So the question is, there is no difference between the top and the bottom. And that observation is correct. This one is the programmer level statement, and this one is it's a statement of the internal data structure that the compiler uses. I just didn't have enough. I didn't know whether drawing all the diagrams or just writing the formula that the compiler internally uses is. So when you're doing type checking, so you turn this into, so this is a universal quantification. So you turn it to an existential quantification by just taking a negation. And then you only work on the non-quantified formula. And you come back with some answer, yes, no, and then you do the negation. That's all. And this is, Pressburger arithmetic is already in your compiler today. Okay. And if the optimizer is using it, it must be good for the type checker too. So I'm going to go over this, and probably the last slide. What I would really like to see going forward is, first, I would like to get to see standard notation in the community to express semantics properties of our library software. And I would like to see more of concepts. I'm tired, I'm tired of iterators. Okay, that has been beaten. Alex did everything. You can do it, but that's all. Okay, we need something different. There are a lot of fields out there that we need to explore so we get better understanding. Okay, I would like to have, to see the community build a repository, a common shared knowledge, just like Boost has built this shared libraries that, people go, and they go to my company, invest in Boost, right? So it must be good. And I would like to see the community build shared repository knowledge that we can all use and have a way to aid semantics our tools, now static analysis tools, or even runtime, as I indicated earlier. So this will be my last slide. Any more questions?
We have a mic up here.
Where is the mic?
We have a mic up here for
yeah,
people ask
okay.
questions.
Just a quick question.
Yes. The question is, why did I call it Liz? So Liz is not, this is not the name of a girlfriend, okay? So the name actually came from my first student who worked on Project Kala. I asked her, okay, we have been working on this for 6 months now. I think we need a better name than The Thing. And she came back with Liz and wanted to make sure that I wouldn't be embarrassed if asked why Liz. And then she told me the story about someone, a little girl she met in the Amazonian forest. She spent 2 weeks there with the family, and she was just, fond of the girl, and the girl was 5 or something, and just she wanted to choose them. I thought that was a good story. I didn't have any better suggestion. All the 3 characters were taken, so unless I had better suggestion, I'll just take it, and yeah.
That's a good name, but
Yeah, it is. Yeah, another question.
Is it purely academic, or is there actually a use case why you developed this?
So the question is whether this exercise is purely academic or whether there is a use case. I started with the idea that I wanted to improve the C++ template system. Right, that's my end goal. So I could do all the work with GCC or Clang or VC++, but I don't have to pay too much attention to distraction. What I call distraction is all the anarchic conversion rules in C++. No, we shouldn't have them. The syntax. I started with syntax, right? Type name, T, colon, template, and then you put your bracket and you feel good. That is distraction. And I wanted just to focus on that, right? So that's why I made lists, but the end goal has always been to improve the C++ template system. And, I gave feedback to Biani and Andrew. So Andrew, when he started, we were all worked together on Concept Light, and the deduction algorithm were taken directly from Blaze, and then he improved it to take, once you want to go to the real world, you have to take into account all those distractions you just didn't want to hear about earlier. So from my view, it is not purely academic. It has end goal. It's very practical. Better this tool that is just awesome, C++. I have 2 more minutes.
Yes. We have here the concept and the model that should satisfy the concept. But it seems to me that this is implicit by the syntax. And only we are stating that we assume that the actions are satisfied. But maybe something that has some syntax that has nothing to do with the concept, or even you can have the same type that could be seen as the same concept, but with different instantiation. How we do take into account these cases?
So the question is, if you look at the list seasonally presented, everything is almost implicit. You have the concept, you have the types, and what actually happens is that the type satisfies the predicate of the concept, and so that is a model. But there is no syntax in language that allows you to manipulate directly the model. Yet it may be the case that you have the same type that will model to concepts, to different concepts. Am I getting that right? Or the same concept differently. So an example for that would be if you take the integers, then integers and plus give you a monoid, and integers with neutral element 0, integers and multiplication gives you monoid with 1 as neutral element. And the question was, would it be good to have syntax? Am I getting the question correctly?
No, it's actually that syntax is not enough.
Yeah, that is. The syntax is not enough, and then you have to map. So that's a very valid point. And as a design decision, based on the experience that I had from the C++ OX effort, it's a conscious decision not to have syntax for the models directly, that the satisfaction should be implicit. This is also in line with what I call automated deduction. It is not the only conceivable design to have, but it is the one I have. Now, when you go back to this slide, you'll see that actually I don't talk about monoid, I talk about monoid structures or monoid operations. So the type itself wouldn't be monoid, it would be the operation. And from that perspective, there is no ambiguity.
Yes, there's choice to talk about the operation and not the type.
Yeah, exactly. So the design just was to focus on the operation. That goes back to the design and the philosophy that if you look at the STL, iterators, there's a lot of things I've been saying and written about the iterators, but they're not the most interesting thing about the STL, right? There are only 4 or 5 of them, categories of them in the STL. What is important is the algorithms, right? And so the design has focused on operation as opposed to on the type. And I want to push that as far as I could to see what breaks and what doesn't work. Because I do believe that having the type, sometimes you actually want to talk about a type, right? But most of the time you want to talk about the algorithm because it's the operations that bring the structure. And I wanted to support that as opposed to, because the other side, we know how it ends. It ends with object-oriented programming, right?